Welcome dears, this is Electrodynamics chapter number 7, Introduction to Electrodynamics by David J. Griffith's book. So our first topic will be Ohm's law. Okay, now let's move to the Ohm's law. First of all, we can see for example we have a conductor here, we have anything here. Okay, this is a charge Q. Now if we want to obtain a current, we want to drive this current, we have to push some force. Okay, and for example that force is F. Now how fast this charge will move in response to this force? Okay, this depends on the nature of the material, which we call conductivity of the material. Let me give you an example of this. For example, here we have two different paths. One, you have to move and cover this pound of water. Okay, and the another is land. Now if you swim or move in this pound of water, you will encounter more resistance. Okay, so it's mean that the conductivity of this material is low, because the same force you apply here and here, you cover a small distance, and here you cover a large distance. But the problem is here that this material has more resistance, due to which the conductivity of this material is low, and this material, the resistance is very low. So this means if the medium is not offering any resistance, this means the conductivity is very high. So this is just the example of how to understand the conductivity of the material, and which we call nature of the material, how fast it will allow the charges to move through them. Okay, now look at the mathematical form of Ohm's law. Here we have J is proportional to F, and F is where F is equal to force per unit charge. Okay, now this force F, okay, this can be gravitational force, this can be Lorentz force, or this can be any force that just move the charges. Okay, any force that causes the charge Q to move. Okay, so now we have to put some proportionality constant here, and this constant, what do you think, what will be the constant of proportionality here? The constant of proportionality is this sigma, this nature of the material. Okay, means how the material is allowing or responding to the movement of charges. So we put here sigma, this is called conductivity of the material, and F, which is force per unit charge. Okay, now this J is a vector quantity and it's point in the direction of this force. Okay, the second thing we have here is, like in general we can see, we drive the charges by Lorentz force. Okay, generally, so we have to put here G is equal to sigma, and this F is, in case of Lorentz force, this F will be equal to Q into E plus V cross B. Okay, these all are vectors, so we have to put a vector sign, and this is divided by a charge. Okay, like here we can see this is force per unit charge. Now this Q and Q will cancel, and the result will be here is J equals to conductivity, and this is E plus V cross B. Now look at this equation. In our general view and our general life, we can see that the charges, let me write the equation again. J is equal to sigma into E plus V cross B. Now if we see the charges in a conductor, like these are the charges, this move with a very small velocity which is called draft velocity, and the magnitude of this velocity is very small. Okay, so when we multiply a very small quantity with another quantity, this will become very small magnitude. So this magnitude will become very small, so we can ignore this term. Okay, we can ignore this. Now the equation we obtain here is just sigma multiplied by E, which is called conductivity, and this equation which we call is equation 1, and this is called, sorry, equation 1 is Ohm's law. Now this Ohm's law is a simplified or a special case of the equation which we have, this is a special case of this equation. J is proportional to F, or we can write it J is equal to sigma into F. This equation explain a lot of stuff. Okay, but now the equation 1 is a special case of this equation. Let me name it as equation 2, and the equation 1 is known as Ohm's law. Now if we look at the application of this equation, okay, significance of Ohm's law in plasmas. In plasma, charges moves very fast. Okay, now the velocity becomes very greater, so you cannot ignore this anymore. Okay, so V cross B term should not be ignored while dealing with plasma. So you cannot ignore this term anymore, and the equation for studying plasmas will be sigma into E plus V cross P. We will deal this equation there. Let me clear another confusion in another slide. Okay, now the confusion is about electric field in conductors. as we see, E equals 0 in conductors, means that electric field inside a conductor is 0. Now this is generally true in electrostatics. Okay, I mean by electrostatics that this is generally true for stationary charges. For example, we have stationary charges here, so the electric field is definitely 0 inside this conductor. But for perfect conductors, for perfect conductors, now what is perfect conductor? Perfect conductors are those whose conductivities approaches to infinity, we can say, mean the resistance is 0 or resistivity is very low or approaches to 0. Okay, for perfect conductor we use by using Ohm's law, J equals to sigma and E. So E will be equal to, by dividing this on both sides, E will be equals to J divided by conductivity. Now conductivity for perfect conductor is infinite, so E equals to J divided by infinity, and this will equal to 0. Now any value divided by infinity is equal to 0. So this electric field is 0 inside, equals to 0 inside a conductor, not conductor but perfect conductor. Okay, conductors, this is equal to 0 for perfect conductors. But what is the case in like we see metals every day, these are also conductor in, I mean, what is the case in ordinary conductors? Okay, in ordinary conductors the conductivity is very high, not infinite but very high. Okay, so when we deal this case for this electric field, when we deal this case for ordinary conductor, the conductivity is very high. This is not infinite, finite, but high value. Now when you divide a small value by a very large value, this will result into a very small magnitude of electric field, and this makes sense. Okay, for example, here we have a conductor. Okay, in this conductor charges are moving, and the resistance is very low, so a small force is enough. You can see that every field applies a force on charge. Okay, a force on charge. Okay, E is equal to F by Q. Okay, so sorry, this I put G everywhere and this is by mistake. E is equal to F by G. Okay, now the field here required is very low, because by applying a very small force, this charge can move a very large distance, or because the resistance is the material offers to the charges is very low. So this makes sense in our daily life, that small electric field in conductors, the electric field magnitude is very small. Okay, and in perfect conductor the electric field is 0. That's the part first of the Ohm's law, and in the next lecture, part 2 of the Ohm's law, we will cover some examples, okay, in which we will derive this equation. V by R, and another equation in which we will see conductivity, and also one another example for conductors, and we have to apply Laplace's equation, and one more general discussion about the drift velocities and why don't charges get accelerated. Okay, so stay tuned, subscribe to my channel, and